Welcome back, Cubs. In this video, we're going to be taking a look at the lecture 10.2 liquids. So go ahead and get your lecture notes ready, and let's jump into it. So, liquids, they only exist in a small temperature and pressure range for each substance. So they're in between the gas and solid temperature and pressure range, which are usually a greater range than the liquids. We all know that liquids have a definite volume and an indefinite shape. So that means if you have a 2 liter of Coke in the original container, it takes the shape of the container. If you open that up and then dump it on your kitchen floor, it'll spread out across the bottom of the floor, taking the shape of that particular container. But the volume itself will remain the same. Similar to gases, the particles are constantly moving about, but the particles are closer together in liquids than they are in gases, and that'll give rise to a couple of the characteristics that we'll talk about on the next slide. So this increased attractive forces, that's usually because of a lower temperature, so lower kinetic energy. Lower kinetic energy means lower movement, but it's still present. This can also be increased by intermolecular forces. So go back and review your intermolecular forces. The big one for this chapter is going to be the dipole-dipole interactions that give rise to some of the characteristics that we see in gases and liquids. So they have a relatively higher density than gases because there are more particles in a particular volume per unit area. So that means that because there's more particles and they are touching, they're relatively incompressible. So we take advantage of this incompressibility of liquids in hydraulic presses. So when you push on one end of the liquid, that force moves through the liquid to perform a function like in brake lines or other hydraulic fluid lines. So liquids are not really compressible because the particles are already touching themselves. Where when we had gases, gases are compressible because of the great distance between the particles within a particular container. Just like gases, liquids can also diffuse. So that means because the particles are in constant random motion, they will mix, but this happens at a slower rate than in gases because of the relative high density. And while they are moving about, they're moving about slower, the particles, that is. Liquids can also undergo something known as surface tension. So if here we have a molecule of water with some other water, there's going to be some attractiveness between the other water molecules. So that's why we usually see water droplets form in a spherical shape because of this surface tension. If you're at home, which you should be right now, go ahead and get a penny and add some water just drop-wise to the top of the penny, and you'll start to see a curved liquid layer form on top of the penny, and that's because of the surface tension. There's the polarity attractedness between different molecules that gives rise to that surface tension. Closely related to that is capillary action. So if surface tension was the attraction between the molecules, capillary action is going to be the attraction between the water molecules and the walls of a particular container, usually a thin tube. This is what gives rise to the meniscus. So when we measure in a graduated cylinder, we want to measure at the bottom of the meniscus, and that's that curve that we see. If the gray here on both sides, that's the graduated cylinder. We have water blue here. This area right here, this is known as the meniscus. And this occurs because of the attractive forces between the water molecules and the walls of the container. So we've seen it in the lab when we use the graduated cylinder to measure. We can also view it in nature. So in addition to the evaporative action of water on the leaves of a tree, it's also this capillary action helps draw water up a tree with in conjunction with the evaporative action occurring at the leaves too. So capillary action, attractive forces between a liquid and a solid. So what about changes, phase changes for liquids? So we've got two closely related terms here. We have vaporization and evaporation. So vaporization is when a liquid or solid goes to a gas, and then evaporation, this kind of explains it a little bit more. So it's particles escaping the surface due to an increase in overall kinetic energy. So when we take the kinetic energy, let's say of this system here, what we're doing is we're taking the average of all of these particles to get the kinetic energy. Some of them will have a lower kinetic energy right here at the bottom in the liquid, and some molecules will have a higher kinetic energy. So the particular molecules with a higher kinetic energy, those can leave the surface from a liquid to a gas form and leave out the liquid, thus evaporating. We also have going from a liquid to a solid, so the formation of solids. So back to kinetic energy. Remember, kinetic molecular theory, one thing we need to keep in mind is the kinetic energy. And that equation was kinetic energy equals 1/2 mass times velocity squared. So we saw here with evaporation that as kinetic energy increases, evaporation occurs. If kinetic energy decreases enough, we can have liquids cooling to a point where the molecules can no longer move about freely and they're kind of stuck in a position. So this solidification is freezing. So it's a physical change of a liquid to a solid by the removal of energy, by the removal of that kinetic energy. So kinetic energy decreases, temperature decreases, the molecule's movement decreases, and they start to become locked in a particular position. When we get to water in section 5, we'll talk about one of the cool ways that water freezes to give it a particular hexagonal structure. Okay, that's it for this lecture. You guys have a couple review questions on page 318. Let me know if you have any questions via email, Remind, or the discussion board. Have a great day, Cubs.